Hello class, how's everyone doing today? I hope you're doing well. Please make sure in this time of isolation, check up on your friends, give them a call, and try to do something positive for yourself every day. You know, exercise when the weather's nice, go out and get some fresh air. I've been getting some projects done around the house in between, getting all this course material ready. Anyway, today we have what should be a relatively short lecture. I'm going to just talk about encoders and priority encoders. And this is page 268 to 269 in the book. And there are two Logisim files online you'll want to download and look at. And so an encoder answers the question, which device is signaling? So if you follow along in the book or just on the notes here, table 5.4, we have a 4 to 2 encoder. That's a C. Normally you'd think there'd be 16 lines with 4 inputs. But in this case, we only need 4 lines to specify how the device works. So here's our inputs. Same for all truth tables. Inputs on the left, outputs on the right. If this line is active, then over here we indicate in binary line 0 is active. If A1 is a 1, we indicate binary, this is the binary value 1. Here we would indicate binary line 2 is active. And here line 3. And so I have a Logisim file that we can look at. And here's our inputs, A3 through A0. Now, a problem that you can initially see here is none of the lines are active, yet the output is 0. We'll fix that in a moment. We can add a line called no requests that indicate that there are currently no requests. And that's a way you can differentiate here. So if line 0 is active, see it's not even connected to anything, the output is 0. Only one of these is supposed to be 1 at a time, which can also cause issues with these encoders. Again, this is just a basic simple concept. Line 1, we have 0, 1. Line 2 is active, we have 1, 0. And line 3 is active, we have 3, 1, 1 for 3. So that's the idea on an encoder. Useful for interrupts in computer hardware. the CPU can look at a binary value to tell which device is signaling. For example, a hard drive may signal once it is done writing data. Hard drives are extremely slow compared to other things in the computer system, and so you want to tell the hard drive, go write this data. I've put it into some fast memory that the CPU copied over to the fast memory quickly, and that's a buffer, and then the hard drive gets to work on it while the CPU goes and does other things, and then when the hard drive is done, the hard drive can signal to the CPU, okay, I'm done, give me another job to do. All right. Priority encoder. This fixes a priority on the request lines in case more than one line is active at a time. And so here's table 5.5. I'm not going to redraw this whole thing. If everything is 0 and the no request will be 1, if everything is 0, nothing is signaling, then the no request output is 1 to indicate that there are no requests, and we don't care what these are. Nothing signaling, so it just doesn't matter. We're not going to look at those. They don't count. Now, if 7 is active, 7 has the highest priority, we don't care what anything else is. Everybody else can be trying to get the CPU's attention, but if this one is active, then it's the one that gets it. And here's what we have, 111 for number 7. If 7 is 0, then 6 is active. We don't care what anything lower priority is, and we have 6 at the output. Here's the formulas you can start looking at. No request is equal to everything knotted together, knotted and anded together. Z0, we have to look across. So Z0 is equal to A4 or A5 or A6 or A7. And it gets slightly more complicated with the other ones. But that's the idea. And of course, I've got a priority encoder that I pulled up. And I've included this in Logisim. This is the built-in priority encoder. Didn't want to have to rebuild it. So this is our no request line up here. I'm going to label that. They don't call it no request, but that's what we will call it. I'll put the label on the west so it doesn't overwrite my text there. This is the enable for the chip, just like with the decoder. And so you can see here, this is a 3-bit output. So this is just one of these guys changed to 3 bits. This is an input right here with 7 bits, and then I use some wiring. I use the splitter. Bit width in, fan out. So there's 8 bits right here on this line, and then the fan out splits it out into 8 separate bits. And so this is my A7 to A0. So you can see here, let's do 0, 1, 2, 3, and we get binary 3 on the output to indicate that 3 is signaling. You see that wire lit up. Now 7 becomes active. It has a higher priority, so our output changes to 7. It doesn't matter what else is on, it's going to stay at 7. 6, 5, whoops, 4, 3, 2, 1, and 0. This just goes to 1 if any input is active. So it's kind of like the opposite of this guy up here. And that's it. That's encoders. If we were doing a face-to-face class, I would tell you that encoders would not be on the test. However, since I'm planning to give you at least a couple days to complete the test, I might put an encoder question on there. But you'll have time to review it. You don't have to memorize anything for the test. It'll be open book. So that's it. Coming up next will be multiplexers in a separate video.